Hi everyone, my name is Yue Yang from UPenn. I will be presenting our paper Visual Goal-Step Inference using wikiHow. This is a joint work with Animus Panagopoulos, Qing Lü, Li Zhang, Mark Yaskar, and Chris Callison-Birch. Let's begin with our motivation. Nowadays, there has been increasing attention on teaching AI systems to understand complex events. One representation of such complex events is called goal-step relationship, which is given a high-level goal, for example, change a tire, and the model needs to infer raise the jack and loosen the nuts are steps to accomplish this goal. Previous studies has investigated this goal-step relationship using text data. However, there can be other modalities in the real world. For instance, when a robot seeing a boiling water, it should be able to infer the user is make tea, make coffee, or cook noodles, and provide useful recommendations based on the inference. Another scenario could be teach a robot to get a slice of cake, which involves the following steps: take the cake out of the box, cut a slice, put it on a plate, and then take the plate to the user. However, these steps are so common sense, no one bothered to write them because of the reporting bias. So it is difficult to learn these steps from the text data. But with the help of multimodalities, it becomes possible to learn these low-level steps from visual signals. Based on our motivations, we plan to learn goal-step relations in a multimodal fashion. As the first attempt to introduce vision in goal-step relations, we propose this novel task, Visual Goal-Step Inference (VGSI), which is defined as given a textual goal, the model needs to infer which image is a plausible step of that goal. For example, on the right side, the goal how to bake fish, the model needs to select image C, which represents an event turning on the oven is a step of bake fish. We consider VGSI is more challenging than traditional text-image matching tasks because the text and objects in the images are not always closely matched. For example, in image C, there is no fish in the scene, but we can still connect it with the task bake fish. Considering VGSI is a novel task, there is no suitable dataset for us to use. So we construct a new dataset from wikiHow. wikiHow is a website that contains a large number of articles on everyday tasks. Each wikiHow article has a goal method step structure. For example, in Figure 2, the article has a goal how to celebrate Halloween during COVID, which consists of 3 methods. For each method, it has a sequence of steps, and each step is associated with an image. We pair the goal and the images as the positive samples of our dataset. In total, our dataset consists of 53,000 wikiHow articles and over 0.7 million images. The detailed distributions and statistics of our dataset is shown in Table 1. We format VGSI as a 4-way choice question, so we need 3 negative candidates as a distractor for each sample. We designed 3 sampling strategies. The first one is random sampling. We just randomly select 3 different articles and pick 1 image from each article by chance. The second one is similarity sampling. We just select the top 3 most similar images of the positive image as the negative samples. The third one is category sampling. We randomly select 3 articles within the same category as a goal. Here are some qualitative examples of our sampling strategies. Before jumping into experiment, let's talk about our methods. The VGSI is formulated as given a high-level goal and an image. We need a model to output the matching score between the goal and image. We have 4 baseline models. First is the device, which projects the feature vector of one modality to another, and uses the cosine similarity to compute the matching score. Second one is similarity network, which is trained as a binary classifier. It has 2 branches to encode the text and image separately and use pointwise multiplication to compute the joint vector. The third one is triplet network, which uses the contrastive loss and trying to minimize the distance between the positive pairs and maximize the distance between negative pairs. The last one is LXMERT, which uses the techniques of transformer encoders and attention layers, trying to ground text with the objects in the image. Since VGSI is a novel task, we want to know human performance on it. We randomly select 100 examples from each test set and ask a pair of annotators to complete each test, and take the average of their scores to reduce the bias. We also did an experiment on the modified VGSI task, just to replace the goal prompt with a method or the step. For example, on the right side, the goal prompt will be replaced by the method improving your diet, or the step eat unsaturated fats. We assume using a more detailed and lower level prompt will have higher performance. We use it to validate that our VGSI task is more challenging. Here are the results. As we can see in Table 2, the best model is triplet network, but it still has a big gap between human performance. For example, in category sampling, the best model is still 29% lower than human performance, which shows VGSI is non-trivial and challenging for the state-of-the-art models. Your XMERT has a very bad performance when using similarity and category sampling, which is because it relies heavily on the grounding objects. But in these two sampling strategies, the objects in the images and the text are not closely matched. Figure 3 shows the performance on the modified VGSI task. Both human and model has better performance when using a more detailed and lower level prompt, like the step, which also reflects our VGSI task is more challenging. One limitation of wikiHow images is most of them are drawings. So we want to know if we can apply the knowledge learned from wikiHow to other real photos. So we select two instructional video datasets, How to 100 Million and Coin, as a target dataset for transfer learning. Since VGSI task is image-based, and we use a keyframe extraction heuristic to select images from videos. For How to 100 Million, we randomly select 1000 goals and pick one video from each goal. And then we use k-means clustering to select keyframes. For Coin, we select 5 videos for each goal for testing, and the remaining videos for training. Since the videos in Coin has already been segmented into short clips by human annotation, so we just randomly select one frame from each clip. To show the wikiHow is superior than the other dataset on VGSI task, we select Flickr 30K and FS Coco for comparison. Here are the results of transfer performance on Coin and How to 100 Million. As we can see, the model pre-trained on wikiHow outperforms the other datasets in both zero-shot and few-shot settings. In some cases, pre-trained on wikiHow without fine-tuning even outperforms the other dataset after fine-tuning, which is a strong evidence that the knowledge learned from wikiHow can be efficiently transferred on the out-of-domain dataset. In conclusion, in this paper we propose the novel VGSI task, which is a multimodal challenge to reason procedural events. We construct a dataset from wikiHow and shows it is non-trivial for certain models. Through transfer learning, we validate the knowledge learned from wikiHow can be transferred on out-of-domain dataset. And we think the multimodal representation learned from our VGSI task can be useful for future applications such as multimodal dialog system or multimodal schema induction systems. Feel free to reach out to us if you think our work is helpful. Thank you.